Hello again. In this video, we're going to go over some extra examples for section 3.2, finding the domains of functions. And so in this instance, they're going to be a little bit more complicated than the ones that I had in some previous videos. For example, if you look at this function, f of x equals square root of x plus 4, and divide by x minus 4. There are some things going on in the numerator and the denominator. And we said before that we don't care if the numerator is 0. It could be anything. However, the square root function applies some restrictions. So first of all, under the square root, we need a value that's non-negative. So under the square root, we have x plus 4, and that should be greater or equal to 0. It's okay if it's equal to 0, but it should not be negative. So it should be greater or equal. And at the same time, we have the denominator that should not be equal to 0. Okay, so we have basically what is called a compound inequality. Both of these inequalities should be true in order for this function to work. So let's go ahead and solve each one. The first one, bringing 4 to the other side, will give us x is greater or equal to negative 4, and bringing this 4 to the other side is going to say x is not equal to 4. All right, so what does it look like? If we were to graph x is greater or equal to negative 4, we have 1, 2, 3, 4 right here. It says that x is to the right of negative 4, and we're including negative 4. So let me use a different color right here, and it goes to the right of negative 4. However, at the same time, it says that x is not equal to 4. So 1, 2, 3, 4. Hello, my kitty is here. She said hello, and now she's gone. Okay, so 1, 2, 3, 4 is right here. And it says that while this is true, also this should be true. X should not be equal to 4. So we're going to take this point out of our domain with an open circle. So, and then, but the rest is good. So we have everything to the left of, to the right of negative 4, excluding 4. So how do we write it? In interval notation, this is going to be negative 4 to 4. And then again from 4 to positive infinity. And we're going to glue those two together. In a set builder notation, open figure bracket, we're describing x such that x is actually greater than or equal to negative 4, and at the same time x is not equal to 4, close parentheses. So that's how the set builder notation looks. This is how interval notation looks. Okay, so the next example. What if you have something like this? You have polynomial in the numerator, polynomial in the denominator. Again, we don't care what's going on in the numerator of this rational function. it has actually, there is a polynomial and there is no restriction on the x values here. But for the denominator, again, we don't want our denominator equal 0. So when does denominator turn into 0? For which values of x? Okay, so we want to find those values and we want to take them out of the domain. In order to find them, we're going to set up this denominator equal to 0 and solve it. Now this is a quadratic equation and we will solve it by factoring. If you don't remember how to do it, refer to the video on review of factoring, and we're looking for two numbers that will multiply to -22 and add to +9, and such numbers are 11 and -2. And if you don't remember how to do this process again, refer to that video. Okay, so this will give us that basically after this, we're going to set each factor equal to 0. So if we have a times b equals 0, then either a or b equals 0. So we have either x plus 11 equals 0 or x minus 2 equals 0. In each case, we're going to have a product of 0. Okay, so let's solve each of these equations. So here x plus 11 equals 0 when x equals -11, and x minus 2 equals 0 is when x equals 2. So either this value or that value will turn the denominator into 0. So we have to exclude those values. So when we write the domain for this function in set builder notation, we could say x is such that, could be anything. The only values that we exclude, x is not equal to -11 and x is not equal to 2. So this is another way to write your domain in set builder notation. For the interval notation is going to be from -infinity to -11, and then from -11 to +2, and then again from 2 to infinity. All right, so that's for this function right here. Now, let's talk about our next example on the list. F of x is a cube root of x minus 1. And we mentioned that before, that the square root function requires a positive, or rather non-negative value under the root. But what about the cube root function? Well, let's think about it. What's the cube root of -1? And I hope that you answered -1 because -1 cubed is -1, right? Let's try another negative value. The cube root of -8, for example, is going to be -2 because -2 cubed is -8. So we conclude that for the cube function, actually, there is no restriction. Negative numbers are allowed for the cube function. So there are no restrictions. A 0 is allowed as well. Cube root of 0 is 0. So for the domain of this function, we're going to say that it's all real numbers, no restrictions. All right. Now let's talk about function where we have x divided by x. This is also a special case. How so? Well, we could say, okay, what's x divided by x? It's going to be equal to 1, right? However, so the x's cancel out. However, when we describe the domain of this function, we still have to take into consideration the denominator and say that x should not be equal to 0. So still, even though the graph of this function will look like the line y equals 1 with a hole at x equals 0. Okay, and let's see if I can illustrate it for you. So here's my Desmos graphing tool, and here I entered my function y equals x divided by x, and so when I point on the line, it gives me coordinates. So for this point, for example, the coordinates are -1, 1, and then I have, let's say here is -0.221. So it is a horizontal line. Basically, it's the graph of y equals 1. But look what happens when I point to this point, 0. And what's the y value? It's undefined. So it actually has a hole in that line at x equals 0. Even though you don't see it right away, but if you were to zoom in or to create a table of values for this function, at 0, the function would be undefined. So the domain is, let's go back to our screen, or paper rather. It is, so x, we could write it in set builder notation. X is such that x is not equal to 0. Or we could also write it, if we wrote it in interval notation, would be from -infinity to 0, and then from 0 to +infinity. All right, so that's this special case. So the point is, even if your values simplify or cancel out, you still have to account for them in your domain. And now let's take a look at this next function. And the reason I picked it out is because it may seem complicated at first, but when you think about it, what are the restrictions? Okay, so here there is no restriction, right? 3 is 3. We're subtracting a square root function, which basically, if we're able to calculate this value, we're subtracting a value from 3, which is not a big deal. Now the question is right here, what are the possible values for x? How are we going to calculate this value? But again, we're looking at a radical function, a square root. And this means that inside of the square root, the value inside should never be negative. So this value inside should be greater or equal to 0 always. And again, like always with radicals, with even indices, we're gonna take whatever's inside and set it greater or equal to 0, solve it, and that's gonna be your domain. So nothing new here. As long as you see the radical, you just set it up like this. Not any radical, but radical with an even index on the root. So that would be your 2 square root of 4, 4th root, or 6, 6 roots. It does not apply to radicals with odd indices like 3 or 5 or 7, it does not apply to those, only the ones with an even index. And this is it for this video, and I'll see you in the next one.